In this video, first we will understand where exactly classical physics fails and see a quick Python simulation which shows the classical collapse. Then how quantum mechanics steps in to reveal why atoms are stable. So we will begin with simple term, charge. A charge creates an electric field, and when this charge moves, it creates magnetic field. And when that charge accelerates, the electromagnetic fields around it change rapidly. So these changing of fields create disturbances, and these disturbances creates a ripple in the space. So we call these ripples electromagnetic waves. Those waves carry energy throughout the space, which is why an accelerating charge radiates and loses energy. All of this phenomenon is elegantly explained by Maxwell's equation of electromagnetism. According to Maxwell's laws, accelerating charge, like electrons in circular orbits, emits electromagnetic radiation. So an electron moving in a circle around the nucleus is constantly changing direction. According to classical physics, it should emit radiation, and due to emitting continuous radiation, it loses its energy. And what happened when it loses its energy? It is spiraling down into the nucleus. Like this, the blue line signifies the electron path and the red one denoting the nucleus. So classical prediction is electrons should collapse. But in reality, atoms are stable. Electrons don't crash into the nucleus. Later on, we solve this paradox by quantum theory. Bohr model introduced quantized orbits or stationary states with discrete energies, stipulating that electrons in these states do not radiate. Emission or absorption occurs only when jumping between allowed states. Electrons can only occupy specific allowed energy states and don't radiate energy while in these states. Anyway, today we will try to simulate electron and nucleus as per classical physics in Python, and we'll see what happens. So first thing first, let's make nucleus in U equal to sphere which have the position vector at center 0 0 0. Okay, okay, a red sphere at origin, then radius equal to 0.3 only for visibility purpose, color equal to color dot red. So a red sphere at the origin, then electron, so electron equal to sphere which have a position vector, position equal to vector, let's say 5.2900. Okay, yes, okay, then radius. Okay, so 5.29 basically this value signifies the hydrogen atom. Okay, so radius equal to 0.05. It's only for visibility purpose. I'm telling again, color equal to color dot blue, let's say. So that means a red sphere at the origin and a blue sphere starting in orbit. Okay, now it's time to set the orbit parameters. So first parameter is radius. Radius equal to 5.29, we already assigned. Then omega. Omega means the angular velocity. Okay, so omega equal to, let's say, 2. Okay, so these values are not the exact values of atom. Okay, so these values I am taking just for visualizing the whole matter, but the inner physics remains same. Let's say decay rate. So the decay rate means how fast the accelerating charge radiates and loses its energy. Let's say decay rate is 0.5. Okay, now it's time for animation loop. So for animation loop, it is equal to, let's say, 0 dt equal to 0.01. Now we are going to use the while loop. So while radius shrinks, so that means, let's say, 0.02. Okay, frame rate I have to give, let's say, 200. That means I'm telling Python not to calculation more than 200 in 1 second for the purpose of visualization. Actually, calculate the time period and velocity. So time period equal to 2 into pi by omega. Understand? Okay. So after time period, velocity. So velocity equal to, it's omega into radius. V is equal to omega r. Then radius. So the new radius is equal to um, decay rate into dt. Understand? Now we have to update the electron position. Now we have to update the electron position. So first time period, then velocity, then radius, and then electron position. So electron dot position equal to vector which have radius into cos omega t. Okay, so basically, see, if you see, we are going to have two-dimensional view of this electron and nucleus. So in two-dimensional, it is the x coordinate is r cos omega t and the y coordinate is r sin omega t. Understand? Radius into sin omega t t. Okay, then 0. So the x value and the y value, and I'm taking z equal to 0 for simplification. That's all. You can do it for three-dimensional also. Now it's time to end the loop. So this is there. Okay, done. Now run it. If everything is well, I think it will. No, something is wrong. Okay, we can see the nucleus, but electron path is not visible. Then okay. So in electron, I have to make another command that make trail equal to true. That means just run it. We'll see it will work on. See it will work. Okay. So here you can see how the electron path shrinks, spiraling around the nucleus, and finally it collapses within the nucleus. If you want to see all the parameters like time, the radius, the time period, the omega, and the velocity, so you can put this command, just this one, that print time, radius, time period, velocity, etc. Okay, so here I'm just explaining the terms. It's a very simple command that is print the time. Let's say time, radius, time period, and velocity. So here the 2f, point 2f, this signifies I want the value of 2 decimal. Here dot 3f means 3 decimal. Run it again and see. See. Okay. Okay. In radius, it is 0.3f. That means it will give the value up to 3 decimal. For the time period, it is also the 0.3f. That means it will give you value up to 0.3 decimal. Okay. So anyway, that's all. So this is the classical simulation of atom. In reality, atoms are stable. In future, quantum mechanics came. The scientist Niels Bohr explained why the atoms are stable, and he found actually the quantized energy levels. If you want to understand the quantum theory of this, just let me know in the comments. I will make a separate video for that.